Yes, I'm back. So we will start with the P block elements. JEE exams, NEET exams are knocking at the door. So you need to do quick revisions of as many chapters as possible. So come with me for this revision. We will take 2 P block elements at a time. We will start with group 13 and 14, finish it off. Then we will do 15 and 16, and then 17 and 18. So let us start. The elements of group 13 are boron, aluminum, gallium, indium, thallium, and nihonium. Let us get you some shortcuts to remember this table. Boron, aluminum, gallium, indium, thallium, and nihonium. These are the elements of group 13, the boron family. So this is, see, no one likes to eat bangan. I bet a few people likes to eat aloo, gajar, in, thela, nahi hai, nahi. So a very few people like to eat bangan, aloo, gajar, in thela. Nahi, mere thela mein nahi rahega bangan, aloo, gajar, in thela. Okay, so this is how we go about these elements. So let us start. Let us start with the general electronic configuration. And what could be the general electronic configuration of these elements? It has to be NS2NP1. What is the reason? That it is filling, all these elements are filling the first block of the P. So it has to be P1. So that's how you remember. The metallic radii of the atoms, they increase, but not regularly on going down the group. The ionization enthalpies of the elements as expected is, yes, they would lose 3 electrons. Why? If you make the elements lose the 3 electrons, you will end up with the inert gas configuration pertaining to the elements. So naturally, for your third ionization enthalpy would be higher compared to the second, compared to the first. And the ionization enthalpy does not decrease smoothly. So if you go down the group, the ionization enthalpy decreases, but it is not smoothly. Then it is boron. See the order, I've condensed it in one shot. Boron, thallium, gallium, aluminum, indium. And why so? Because of imperfect screening or shielding, thallium has a higher ionization enthalpy compared to gallium. So there's an interchange between gallium and thallium because of the ineffective screening or shielding of the electrons. The electronegativity, yes, the electronegativity of the elements, they would decrease from boron to aluminum, and then it will increase slightly till thallium. So there's a trend that you need to remember because these are based on results which were obtained after experimentation. So if you see the most common oxidation state, yes, you have guessed it right, the most common oxidation state would definitely be +3 pertaining to the NS2NP1 configuration. But remember something called the inert pair effect. The inert pair effect means as the shells grow bigger and bigger in size, the NS2 electrons, since they are pulled towards the nucleus, they tend, because of imperfect screening or shielding, they tend to share or lose only 1 electron. So +1 oxidation state persists as we progress down the group, and that is called inert pair effect. So if you see for indium, we would expect the +1 oxidation state to be dominant. Going on to the chemical properties, whatever I found important, I picked it up and displayed it in my screen so that you can quickly revise group 13 without wasting a lot of time. Let's go to the chemical properties. All these elements, because of the common +3 oxidation state, would form the trioxides, or definitely form the trioxide. So any of these elements, if you react with the oxygen, it will form the trioxide. All right. Now, for example, if we go to the nature of boron oxide, it is acidic. Aluminum and gallium oxide are amphoteric. Indium, thallium oxides are basic. Notice the +3 oxidation state for thallium and the +1 oxidation state for thallium, both are basic in nature, though the +1 oxidation state is dominant. Okay, going to the next one. All these elements do not react with nitrogen. Only boron and boron react with nitrogen. Why does only boron, not only boron, even aluminum to some extent react with nitrogen? Because these elements are small. Nitrogen being small in size, the overlap is good. So boron and aluminum form the nitrides of the formula En. Both are trivalent, be it aluminum or be it boron, they're trivalent. So the boron trinitrides have the formula En. Boron, they do not react with acids and alkalis. Okay, they don't, because of the small size. But aluminum dissolves in mineral acids and alkalis because it shows its amphoteric character. If you use nitric acid in aluminum, you will get an oxide layer. The aluminum will be rendered passive because of the formation of oxide layer. So these are things to remember. If you feel that I'm going fast, you can pause the video. You can make notes for yourself and carry on. And one thing I would tell you, please write down all the reactions. Take a pen and paper, write down the reactions at least once. That will, put things inside your head permanently. I assure you that. Let us go to the next. These elements react with halogens to form the respective halides. And these halides, because their octet is not complete, because these halides octet is not complete, they would all behave as Lewis acids. Let us take, for example, aluminum chloride. Let us, for example, take aluminum chloride. Aluminum chloride will behave as a strong Lewis acid because its octet is incomplete. So these trihalides are basically covalent, they are electron deficient, and they behave as Lewis acids. Okay, but their Lewis acidic character decreases with increase in size down the group. Going on to the important compounds of boron. Orthoboric acid. Orthoboric acid, formula H3BO3, it is also a white crystalline solid. And when you play a carom, yes, you would use this carom board to make the board slippery. So this is what you use, boric acid. It's a white crystalline solid with a soapy touch. And how is it prepared? Put borax in hydrochloric acid with water, it will definitely form boric acid. So boric acid, an important question. I warn you, this is an important question. Whatever I'll speak next. Boric acid is not a protonic acid. That means, though we are calling it an acid, the acid itself does not give out the proton. But you know that all acids express its acidic characteristic in water. We have to put it in water. So what boron trihydroxide does, what does boron trihydroxide does? It tends to form the tetrahydroxyborate complex, giving out the H plus from water. Yes, that is why we call it an acid, but not a protonic acid. BOH thrice accepts a hydroxyl from water and gives out a proton, which has been written as a hydronium ion for you. I hope it is clear. Next important questions, mind it, yes. So going on to diborane. Diborane, you can write it as BH3 also, but usually it exists in the dimeric form, and that is why it has been written as B2H6 instead of BH3. How is it prepared? You put boron trifluoride in a hydride-rich compound, lithium aluminum hydride, sodium borohydride. So let's take the first one. If you take boron fluoride, boron trifluoride, and treat that with lithium aluminum hydride, which is a good reducing agent, a good hydrogen supply, you land up with B2H6. And obviously the side products are lithium has to go out as the fluoride and aluminum has to go out as the fluoride. Easy. It is very easy. But in the lab, we need easy chemicals to work with. So you have sodium borohydride reacted with iodine. You have B2H6 with NaI and H2. This is how in the lab diborane is prepared. Next, also you require diborane in a number of reduction reactions. So how is it prepared in the industry? BF3 is reacted with NaH, sodium hydride, at 450 Kelvin roughly. It gives you diborane along with sodium fluoride. I'm going on to the structure. Now, when we have diborane, You know, because its octet is incomplete, one boron has 3 hydrogens. Here it is one boron with 3 hydrogens. So you have an empty p orbital in boron. This empty p orbital in boron tends to accommodate a pair of electrons from the neighboring BH bond. The boron, you know, it has an empty p orbital. It tends to accept a pair of electrons from the neighboring BH bond and form a bridge compound or a banana bond, where we call it a 3-center 2-electron bond. The 3 centers involved are B, H, H, and the next H. Sorry, the 3 atoms involved are B, H, and the other H, which is transferring its electron to this boron. So this is one 3-center 2-electron bond, and the other one is B, H, and the other H, which is transferring its electron into the empty orbital of boron. So we have the second 3-center 2-electron bond. So if you see, there are 4 normal, we have 4 normal BH bonds. We have the 4 normal 2-center 2-electron bond, which is a normal covalent bond lying in the same plane, and we have 2 bridge bonds, which is the 3-center 2-electron bond. So this is the structure of diborane. So it has alternate boron, nitrogen, boron, nitrogen, and each of these have a hydrogen. So this is your inorganic benzene, which is called borazine. And how is it prepared? Put ammonia in diborane and you get your complex. This complex, you can write it BH2 NH3 whole twice plus BH4 minus, which is a complex which is formed, and then you heat this complex, you land up with your borazine, which is B3N3H6, giving out 12 molecules of hydrogen. Okay. So we can prepare a number of boron hydrides. One of them is sodium borohydride. And how is it prepared? You take sodium hydride. You take sodium hydride, heat it with diborane, and you get M plus BH4 minus, means Na plus BH4 minus. Or you can prepare your lithium hydride also. Continuing with the method of preparing borax, which is from calcium borate, Ca2B6O11. You add sodium hydroxide, you get borax, Na2B407 with sodium metaborate and calcium carbonate. Borax is actually found in nature, so you can just extract it from nature and then purify it. Going on the properties of borax, if borax is treated with water, then it forms boric acid, H3BO3, along with the side product is sodium hydroxide. Borax, when heated, it gives out the 10 molecules of water and gives you the dehydrated borax. Borax, when further heated, it gives you sodium metaborate along with boron trioxide. And the dehydrated borax, when treated with concentrated sulfuric acid with a few drops of water, 5 molecules of water, it gives sodium sulfate and boric acid. So you have 2 methods of preparation of boric acid. One is just heating with water, or just or without water. It requires a few drops of acid and gives you this boric acid. Boric acid, when treated with ethanol, gives you triethoxyboric. So these are a few important reactions of borax. And now we'll go on to group 14 elements, our carbon family. Of course, you know this because it is very, very easy. So this is carbon, silicon, germanium, tin, lead, and flerovium. So this is my cutesy Geeta, sings Punjabi fluently. So this is my cutesy Geeta, sings Punjabi fluently. And let us go on. The general electronic configuration will be NS2NP2 The covalent radii will definitely increase down the group, but the difference in covalent radii between silicon and germanium is less, as once again germanium has a fulfilled 3D shell which shields the nuclear charge effectively, and if it shields the nuclear charge effectively, then the radius would squeeze down. It would not be that much as expected. Okay, now going on to the ionization enthalpies. The ionization enthalpy of carbon, silicon, germanium, tin, and lead. Tin and lead. Can you see tin and lead? Yes, have you noticed? Tin, germanium is greater than tin, and lead is greater than tin. So remember this order. Electronegativity. In case you've missed something, you can definitely pause, rewind, and go back. And I hope you're writing down your equations. I've not given much. There's not much equations also. The electronegativity values will definitely should have decreased because they're becoming metallic, but silicon to lead are almost same, Okay, the most common oxidation state expected is +2 and +4 because of the general electronic configuration NS2, NP2. And as we go down the group, the +2 oxidation state persists because of, yes, you said inert pair effect, you already know it. So the +4 oxidation state decreases for germanium to lead, while the stability of the +2 oxidation state increases from germanium to lead. Let's go on to the chemical properties. Once again, we discuss the oxides. React any metal with the oxygen and you will get the respective oxide, be it a monooxide or a dioxide. Let's go to the acidic oxides, carbon dioxide, silicon dioxide, germanium dioxide, and the amphoteric oxides. This is something that you need to read in your head. You can write it down, put a highlighter that this is to be learned by heart because it is totally experimental. Where is the time to do experiments? No. So write it down. SNO2, PbO2 amphoteric, CO is now neutral, GeO is acidic, germanium oxide, monooxide is acidic, tin monooxide, lead monooxide are amphoteric, and silicon oxide exists at high temperatures. Okay. So carbon, silicon, and germanium are not affected by water, but yes, if you want to react tin with water, you can do it, but you have to have steam. Then it'll form the oxide and give out hydrogen gas. Lead is unaffected by water. Thankfully, the water at our homes is being carried by the lead pipes. So yes, it should not react with water, but it forms a protective oxide layer and it remains there, and water flows safely from the source to our homes through those lead pipes. The group 14 element halides like MX2 or MX4, they are covalent, except, when I say except, that is where you need to take your highlighter and note it down. So what are the exceptions? What are the exceptions? When I say except, most of the MX4 are covalent in nature except SNF4 and PbF4, which are ionic. You know, fluorine being the most electronegative element in the periodic table has a lot of polarizing effect, and it polarizes the cloud to such an extent that it totally increases the ionic character and decreases the covalent character if I'm observing Pajan's rule to its best. Let's go to CCl4. Except CCl4, the other tetrachlorides are easily hydrolyzed by water because of the availability of d orbitals. If d orbitals are available to the space is available, then the hydrolysis can happen for all the tetrahalides excepting CCl4. And you already know from your 9th standard, 10th standard, that carbon shows the property of catenation, means self-linking through covalent compounds forming long chains and also ring compounds. That is not new to you. Order of catenation, carbon, much, much higher compared to silicon, greater than germanium, equal to silicon. And you know about diamond, you know about graphite, you know about fullerenes. I think I don't have to tell you much, but these are the few things that you can just go through it, pause, read it. You must be knowing about fullerenes, no? That it forms 60 membered carbons, like it was designed, and It looked like a soccer ball with alternating 6-membered and 5-membered rings. So amorphous allotropes of carbon are carbon black, coke, and charcoal, or impure forms of graphite or the fullerenes. Some important compounds of carbon and silicon are carbon monoxide. If you want to prepare it, put carbon and insufficient supply of oxygen, you'll get carbon monoxide, which is definitely odorless, poisonous, colorless, and water insoluble gas. If you want to form carbon monoxide, be careful while you're working with formic acid. If you're dealing with formic acid, because if it is heated to 100 degrees Celsius under concentrated sulfuric acid conditions, you get carbon monoxide also along with steam. Coke, if heated with water, see the temperature, approximately 450 to 1200 degrees Celsius, gives you a mixture of carbon monoxide and hydrogen, which is called water gas. And carbon, when heated with air, which is a mixture of oxygen and nitrogen, the carbon takes up the oxygen, forms carbon monoxide. Nitrogen remains in the mixture unreacted, and this is called producer gas. All right, and it is a powerful reducing agent. And be carbon monoxide, it is used in metallurgy to get the respective metals from its oxides. You know that about carbon monoxide. Carbon monoxide, it is used as a ligand also, ligand. It forms nickel tetracarbonyl, chromium iron pentacarbonyl, chromium hexacarbonyl, so on and so forth. You must have done in your coordination compounds. So carbon monoxide acts as a donor and forms metal carbonyls. Carbon monoxide is also an important fuel. It is used in water gas, producer gas, coal gas, but it is toxic and it forms carboxyhemoglobin. Yes. So that is one disadvantage of carbon monoxide. Going to carbon dioxide, I don't have to tell you that if you want to get carbon dioxide from coke, carbon, give excess of oxygen and you'll get carbon dioxide. Heat methane and oxygen, and it's a combustion reaction where you get carbon dioxide and water. On a commercial scale, it is prepared by heating calcium carbonate, and you can definitely get carbon dioxide from calcium carbonate and HCl, acid plus base, salt plus water plus carbon dioxide. It is an acidic oxide. Carbon dioxide is an acidic oxide, and it reacts with bases forming salts. Solid carbon dioxide is also called dry ice, which is used to freeze food and ice cream. It is not poisonous, but its excess inhalation may be fatal for health. It is used, or it is a greenhouse gas. Going on to silicon dioxide, it's commonly called silica, and it is widely found as sand and quartz. Of course, SiO2 is also a three-dimensional network where it forms an 8-membered ring of SiO, 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 SiO. So this is how, I've drawn only one framework of the three-dimensional network. And that's the reason it has got very high melting point. So it is almost non-reactive, but it reacts with HF. It reacts with HF to give you silicon tetrafluoride with the side product is water. And if you react silica with sodium hydroxide, you will get sodium silicate, which is used in the glass and the paper industry. You require sodium silicates for your glass and paper making. Next, going on to the preparation of silicones. When chloromethane is treated with silicon in presence of copper powder at 573 Kelvin, it gives you the dimethyl silyl chloride. So dimethyl silyl chloride, when hydrolyzed, it gives you this dihydroxy dimethyl silane, which is used for the preparation of the polymer, which is SiCH3CH3O repeated a number of times. Okay, so this gives you silicone, which has a lot of pharmaceutical uses as well as in the cake industry. So before we wind up, yes, MCQs. So these are the MCQs which I have displayed for you. You may find some answers being given to you. So this is a practice sheet. This is the practice sheet, MCQs. I have solved maybe a question or two. Yes, so this is displayed for you, and we will discuss the answers. Pause the video, you can take your answers, keep it ready for the next episode to be aired, where I would be discussing group 15 and 16. And before we discuss 15 and 16, I would give you the answers. Why? Look, go to Google, wait for my next episode, and you will see the answers. And you can cross-check how much marks have you got out of 20. Okay, so you can just pause the video and then you can check out your correct answers. Thank you for watching, and do look out for the group 15 and 16 being aired soon. Thank you.